Okay, so we are discussing about elastic failure theories. So in that we already seen maximum normal stress theory or maximum principal stress theory, or we'll call that as a Rankine theory also. So in case of maximum normal stress theory, the failure is predicted based on the maximum normal stress. So that is if the magnitude of that maximum normal stress exceeds the yield strength of the material, then we can say there may be a failure. So in order to define the component based on that maximum normal stress theory, always you need to make sure that the maximum normal stress induced in the component should be less than this ultimate yield strength, ultimate strength, or maybe the yield strength. So generally we discussed that point also. This maximum normal stress theory is valid, or it will predict proper results or good results in case of brittle materials only. So in case of ductile material, that is not going to show proper results. So that means whenever there is a brittle material design for the brittle material, we'll choose maximum normal stress theory. Then we discussed about the maximum shear stress theory. So in this, we already derived the equations for failure for state of biaxial state of stress, or even for triaxial state of stress also we derived those equations. So then we plotted the curve for biaxial state of the stress. So now the curve is going to be the hexagonal here. So in case of maximum shear stress, it is going to be hexagonal shape. So whereas in case of maximum normal stress, it is a square or rectangle. You can see there are 4 sides. Here you have 6 sides here. So now these are the equations we already seen in the yesterday's class. So these are the failure equations. Sigma 1 minus sigma 2 is equal to SYD by Fs. Sigma 2 is equal to SYD by Fs, and sigma 1 is equal to SYD by Fs. Now if you look at these equations, in all the equations I am using only SYT. I am not using SYT. I am using only SYT. So in these equations you cannot see SUT. So that means this theory is suitable for ductile materials. So it is not suitable for brittle materials. So generally in case of brittle material you have ultimate strength. You don't have well-defined yield strength. We'll take ultimate strength as a failure criteria, whereas in case of ductile material we'll take SYT as a failure criteria. That means, so in the design equations if you have SYT means this theory holds good for ductile materials. So or in our design equation you have SUT, then that theory holds good for brittle materials. So now see, now this is our failure envelope for this maximum shear stress theory under biaxial state of stress. Now if my point or my design point lies within this envelope, then the design is safe, or else if the point falls outside this envelope, the design is going to be fail. So that is the failure criteria. So that's what I written here. In case of biaxial stress, if point with coordinate sigma 1, sigma 2. So we plot this curve on sigma 1, sigma 2 axis. So if it is if you plot the curve, or if you plot the point with coordinates sigma 1 and sigma 2, which falls outside this hexagonal region, then it indicates the failure condition. On the other hand, if the point falls inside the hexagon, the design is safe and the failure may not occur. So that means always while designing a component based on this maximum normal stress theory, now you need to find out for the given component under the given load, you need to find out what is sigma 1 and sigma 2, and you need to mark the location of that point on this sigma 1, sigma 2 axis. If that point lies within this envelope or on the envelope, on this line also it is safe. If it falls outside, then the component is going to be failed. So this is about this maximum shear stress theory. So the maximum shear stress theory of failure is widely used by the designer for predicting the failure of components which are made of ductile materials like transmission shaft. So that means here, like I already told you, so this theory will be mostly used for ductile materials. So it is not used for brittle materials because this may not predict proper results in case of brittle materials. So this theory is most applicable for ductile materials. So then we'll move on to another theory. So first we say maximum normal stress theory, then maximum shear stress theory. Then another theory is distortion energy theory. So this distortion energy theory was defined by this person von Mises. So that's why it is also called von Mises theory also. Distortion energy theory or von Mises theory, or sometimes it may be called as Henke's theory also. So whatever may be the name it is called, the concept is the failure is based on the total distortion energy. So if you are able to calculate the distortion energy in the body, then if the distortion energy is equal or greater than the distortion energy of a specimen which is subjected to a simple tension test, then failure will occur. Otherwise, the component is going to be safe. So, okay, so it is known as Oberon Mises. Sorry, it is von Mises, and it's not on. It's von Mises. Here this V missing here. Von Mises and Henke's theory. So the theory states that the failure of mechanical components subjected to biaxial or triaxial state of stresses occurs when the strain energy of distortion per unit volume. So this is what we'll call it as a distortion energy. Strain energy of distortion per unit volume. That is nothing but the strain energy density of distortion. That is why we'll call it as a distortion energy at any point in the component. So the strain energy of distortion per unit volume at any point in the component becomes equal to the strain energy of distortion per unit volume in the standard specimen of tension test when yielding starts. So this is the failure criteria in case of distortion energy theory. So that means in case of distortion energy theory, what we need to do is first we need to compute what is the distortion energy or distortion strain energy. So strain energy is nothing but when you apply load to the body, it will deform. So upon deforming, it will store some energy. That energy we call it as a strain energy. So that's why it is called distortion strain energy. So simply you can call it as distortion energy also. It doesn't matter. So now here you need to calculate what is the distortion energy per unit volume in case of a component which is subjected to biaxial or triaxial state of stress. That is one condition. Or one side of the equation is that. So that means whatever there, whether you have a biaxial state of stress or triaxial state of stress, for that you need to compute what is the distortion energy per unit volume. Then you need to take this and you need to compare this strain energy, distortion strain energy to the distortion strain energy of a standard specimen of tension test at yield point. So that means you need to calculate the distortion strain energy in the two cases. One is for the actual biaxial or triaxial state of stress system. Other one is in a case of simple tension test at yielding what is the distortion energy. So now by taking these two and if you equate these two, that is the failure condition. So in order to avoid the failure, so maybe the distortion strain energy in the given actual condition should be less than the distortion energy of the standard specimen of that simple tension test. So then at yield point, so then based on that you can derive your design equations and you can write the equation. So for that what we'll do is first we'll try to find out what is the strain energy of distortion per unit area in case of triaxial state of stress. Then from this triaxial state of stress I can find out what is the distortion strain energy for a biaxial state of stress, even in case of the simple tension test also. Simple tension test we know it is a uniaxial loading or uniaxial state of stress will exist in case of our simple tension test. That means if I know the expression for distortion energy, generally strain energy is denoted by U, so I will use distortion strain energy is UD. So if I am able to find out this UD for triaxial state of stress, so from the same thing I can derive it for the biaxial as well as this simple tension test also, all the three conditions. So that means, so once I am able to derive the distortion energy expression in case of a triaxial state of stress, I can derive the expression for all, then I can write the failure theory also. So before going to derive that, first you need to understand what is this distortion energy. That is also important. So distortion energy means, so we know strain energy nothing but when a component, suppose if this component is subjected to some tensile force, let us say P. So because of this P, we know there is a normal stress sigma in this, and because of this tensile stress, the length of this component will extend, or the length will increase. That means this bar will elongate. So because of elongation, you have a normal strain also. So the normal strain, so the strain energy is nothing but the amount of energy stored in the body upon elongation. So that we'll write it as half into sigma epsilon. So this is the strain energy density, you can call it as strain energy per unit volume. Here I said it is strain energy per unit volume. So unit volume means, see, if you take the units of this, what are the units going to be for this? So here half, okay, half stress units, stress is having units of either Newton per mm square or Newton per meter square. Okay, let us take it as Newton per mm square. Sigma. So this is sigma. I am writing U. So U is equal to half into sigma into epsilon. If it is a uniaxial, see, I am taking a only uniaxial load here. So then epsilon, we know strain is nothing but dimensionless. So therefore, what are the units for this? See, it is Newton per mm square. But I am saying this one is strain energy density. Density means by volume. I am dividing this one by volume. So capital U divided by V. So that means, so this is divided, if I divide this one by volume, which is volume units are mm cube, what I am going to get it is Newton mm only. So then this is what we call it as energy. So energy is Newton mm or Newton meter can be expressed as joules. Joules is nothing but the unit of the energy. So that means if you write half sigma epsilon, this is the strain energy stored per unit volume of this member. So then similarly I can calculate, this is the case for a uniaxial stress. So, but I want to calculate it for the triaxial state of stress. So in that case, how we can take it is, we will take the stress element and we'll try to find out what is the first strain energy. From that, then we'll define what is distortion strain energy. So then we'll try to find out the expression for the distortion strain energy also. So for that, to compute the strain energy, first I'll take a triaxial state of stress, something like this. I have a stress element. I can represent the stress element by taking an elemental cube in the at that point where I am going to calculate the strain energy. Now I taken the three principal planes here. This is the sigma 1 direction, and this is the sigma 2 direction, and this is the sigma 3 direction. So now, because of the sigma 1, sigma 2, sigma 3, what happened to this component is, so in some place there may be shear stress, maximum shear stress. Sometimes there may be a normal shear stress. That means, so two things is going to happen here. So one is, definitely we know because of this applied load, the volume will increase. The volume of this cube, before applying the stress values, it is one volume U naught if I take. So then definitely the volume of the component will change. So I'll take that one as dV. So then, so here two things. So the volume will change. Another thing is going to be, so the shape. So before applying the load, it is actually it is a cube. So but because of this applied load or applied stress, its shape may be also distort. So then that I will call it as the energy which is causing the distortion in the shape of the component, we call it as a distortion energy. So that means I am dividing that one into these stress components into two components, something like this. I shown it here. So here this is the axial loading system. So I am splitting this one is into two parts. One is causing only the volumetric change. That means there won't be any change in the shape of the cube. So the cube remains same, but only thing is its volume will change. So whatever volume it is changing here, the volume change of this block is also same. So that means the volume change of this block is 0. dV of this block is 0 under this stress system, and dV of this one is dV. So for this loading system also, let us say the change in volume is V, dV. So therefore this dV is same, but because of this stress there won't be any change in the volume. So that means now if I club these two are equal. But so this is, even though because of this one, so you don't have any volumetric change, there may be change in the shape. So here, let us say if I take the cross-sectional sphere here, it may become something like this. So with the same dimensions, but only thing is the cross-section will change, something like this. It will going to distort, means deviate from the original shape. So therefore, so I can split this condition as this one and this one. So now what I need to do is, whatever may be the strain energy, total strain energy here, if I take that one as the total strain energy, I can write this one as U is equal to, so this is the distortion strain energy UD, and the strain energy stored in the block because of this volumetric change, so I'll call it as UV. So that is, here only volume is changing, but there is no change in the shape. Here there is no volumetric change, but only thing is the shape is distorting here. So therefore, since the distortion of shape is there, here also energy stored and here also the energy stored. So but for our design criteria, we require this UD. So from this equation I can write UD is nothing but distortion strain energy is nothing but the total strain energy, this U, minus this volumetric strain energy due to volume change. So UV. So that means, so directly I cannot compute here this distortion energy because here there won't be any volumetric change. So but I'll make by calculating this one and this one, I can calculate the distortion energy using this expression. That means I need to compute what is the total strain energy and I need to compute what is the strain energy for only volumetric change. So now we'll see how we can derive these two. From this, how we can derive this distortion strain energy also. So now for that, first I want to compute what is the strain energy of this one. Then if I subtract the strain energy of this block from this block, I will get this. So for that, first I am calculating the strain energy of this block. So here we know three principal stress. It is subjected to sigma 1, sigma 2 and sigma 3. Just now I showed you in case of uniaxial load, this is the expression for the strain energy density. So, but here we have tracked the state of stress. So therefore strain energy due to sigma 1 is this one and strain energy due to sigma 2 is half into sigma 2 into epsilon, and strain energy due to sigma 3 is nothing but half into sigma 3 into epsilon 3. So but here what we'll do is I'll try to convert or I'll try to substitute for epsilon 1, epsilon 2 and epsilon 3. These are epsilon 1 and epsilon 2, epsilon 3 are nothing but the strains, normal strains in the x direction. The sigma 1 direction is epsilon 1 and the normal strain in the sigma 2 direction it is epsilon 2 and the normal strain in the sigma 3 direction is epsilon 3. See, epsilon 1, epsilon 2, epsilon 3 are normal strains, and also we have a relation between these normal strains, or we can say principal strains also we can call it as, because there is no shear stress here, principal strains. So we know the relation between principal strains and principal stresses. So those relations are here I have shown. So epsilon 1 is given as 1 by E into sigma 1 minus mu into sigma 2 plus sigma 3, where E is the Young's modulus of this material of this cube and nu is the Poisson's ratio. So similarly I can write for epsilon 2 and epsilon 3 also. So this is the expression for epsilon 2 and this is the expression for epsilon 3. So epsilon 2 can be written as 1 by E into sigma 2 minus mu into sigma 1 plus sigma 3, and epsilon 3 is equal to 1 by E into sigma 2 minus mu into sigma 2 plus sigma 1. So now once I know these relations, expressions for epsilon 1, epsilon 2, epsilon 3 in terms of sigma 1, sigma 2, sigma 3, I'll substitute back these three expressions into this expression in the strain energy, and I'll replace epsilon 1, epsilon 2, epsilon 3 by sigma 1, sigma 2 and sigma 3. So if I do that, so I'm going to get this is the expression, and if I simplify that expression, I'll get this is the expression for the strain energy, total strain energy. You can say it is total strain energy of in the cube, that elemental cube. So it is, which is equal to 1 by 2E into sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 times nu. Nu is the Poisson's ratio, sigma 1, sigma 2 plus sigma 2, sigma 3 plus sigma 1, sigma 3. So, but we don't want this. Okay, we want this, but still we require one more quantity, that is the strain energy because of volumetric change also required. So that if you use these two, then if you subtract the strain energy due to volumetric change minus the total strain energy, then only you will get the distortion energy. So for that we need to compute that also. Okay, that's what I written here. The total strain energy is resolved into two components. First UV corresponding to the change of volume with no distortion of the element. So that's what we already discussed. UV is corresponding to only change in the volume, but there is no distortion in the element. And the second one is UD corresponding to the distortion of the element with no change of volume. So therefore, I can write U as UV plus UD. So from this, I can write UD is equal to U minus UV. So to compute this UV, what we need to do is, like I already shown to you earlier, the stress components are also resolved into two components. You see, if you see these figures here, see here, the sigma 1 is resolved as, so if I say this is equal to this, means, so if I superimpose one upon another, that is, if I use the principle of superposition, from this I can write sigma 1 is equal to, so the stress is sigma 1d plus sigma v, sigma 1d plus sigma v. Similarly, sigma 2 I will write it as, sigma 2 is nothing but this one is equal to these two components, this one plus this one, that is sigma 2d plus sigma v. Similarly, sigma 3 equal to sigma 3d plus sigma v. So that means if I add all the three, sigma 1 plus sigma 2 plus sigma 3, so then what I'll get, the summation of these three is nothing but, so this side, right side, what I'll get is, you have sigma 1d plus sigma v, sigma 2d plus sigma v, sigma 3d plus sigma v. So that means sigma 1d plus sigma 2d plus sigma 3d plus 3 times sigma v you will get. So because sigma v is there for all the components. So here 3 components of sigma v is there. So that means I need to sum up these 3 and I need to sum up these 3. If I sum up these 3, sigma 1d plus sigma 2d plus sigma 3d plus sigma v plus sigma v plus sigma v in equal 3 sigma v. So this side you have, left side of the equation is sigma 1 plus sigma 2 plus sigma 3. So now, so using this relation also, so you have this 3 sigma v is there. So now I want to compute what is the volumetric change, what is the strain energy for because of the sigma v. So I use these expressions to calculate that. So that I will show in the next slides. See, now I'll come here. Okay, so this we already seen. Okay, right. So like this, we are splitting the stresses also. Sigma 1 as sigma 1d plus sigma v, sigma 2 as sigma 2d plus sigma v, and sigma 3 as sigma 3d plus sigma v. So then the strain energy UV corresponding to the change of volume of the cube is given by like this. So how I got this? So just simply I have an expression for strain energy in case of a, this is the expression for the strain energy of the, so this is the expression for the strain energy when it is subjected to sigma 1, sigma 2, sigma 3. But now in case of this volumetrical change, so in this case, in third case, this is the case. I want to calculate what is the strain energy for this block. So for that, here your sigma 1 is equal to sigma v, and sigma 2 is also equal to sigma v, and sigma 3 is also equal to sigma v. So that means, so whatever expression I got it here, so in this expression I need to substitute sigma 1 is equal to sigma 2 is equal to sigma 3 is equal to sigma v. So if I substitute, what I'll get? So here 3 sigma v square, then here sigma v square, here sigma v square, here also sigma v square, because your sigma 1 equal to sigma 2 equal to sigma 3, which is sigma v only. So this is also, what I'll get is 3 sigma v square. So if I take 3 sigma v square common throughout, then what I'll get? 1 by, or in place of 1 by 1, I'll get 3 sigma v square divided by 2e into, so here what I'll get? I have only 1. Here I have 1 minus 2 nu. So this I need to get. So, but what is the sigma 3 sigma v square? So just now we have seen that sigma v, 3 sigma v also, those relations also. So now you need to substitute those relations also, so that you will get the expression for the strain energy. So now, okay, so if okay, I'll do that here. See, if I do that, you will get, this is the expression for, so, okay, so here I have shown you are getting a, okay. Okay, I'll show it here. How we got that. So for this, okay, I'll write this as UV as, so if I substitute sigma 1 equal to sigma 2 is equal to sigma 3 equal to sigma V, then what we are getting is 3 sigma V square divided by 2 times E into 1 minus 2 nu. 2 times nu. So this is what we got it. So but I want to find what is the sigma V square also. So for that, how I can calculate sigma V square? Just now we derived it. So sigma 1 plus sigma 2 plus sigma 3 is equal to sigma 1d. So that means I am adding up all the stresses. Sigma 2d plus sigma 3d plus 3 sigma v. So now if I square this, so I need to square this side also. So or else what I'll do is I'll try to find out what is the volumetric change. So what is the strain energy also, or in that way also you can do it, or else like this also I can do it. So if I try to simplify this, if I square this, so this, then if I simplify this, I'll get those two relations. If I use those two relations, so I'll get, this is the equation for this volumetric strain. So 1 minus 2E. So here that 3V square can be represented by this one, sigma 1 plus sigma 2 plus sigma 3. So V square, sigma V is nothing but what you are going to get is sigma 1 plus sigma 2 plus sigma 3 divided by 3. So this is the relation you are going to get. If you simplify those expressions, you get your sigma V as sigma 1 plus sigma 2 plus sigma 3 by 3. So then if I substitute that here, what I am going to get is, this is the expression for that sigma strain energy for, because of only volumetric change, there is no distortion. So now I have expression for U and I have expression for UV. So I'll subtract UV from U so that I'll get the expression for UD. So that's what I did here. So then if I substitute into this expression, this is U and this is UV, and if I subtract and simplify that expression, so this is the total distortion strain energy per unit value in case of a triaxial state of stress. So now I have an expression for distortion strain energy per unit value in case of a triaxial state of stress. So now if I want to derive for biaxial state of stress and uniaxial state of stress from this expression, what we need to do is, suppose for biaxial state of stress, only thing I need to do here is I need to put sigma 3 equal to 0. In case of biaxial state of stress, you have only sigma 1 and sigma 2, sigma 3 is 0. So in that case, what you are going to get is your UD is equal to 1 plus nu by 6E into, so here you will get this one as same, sigma 1 minus sigma 2 whole square, because both are non-zero values, sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3. So this sigma 3 is 0. What you are going to get here is sigma 2 square. Then sigma 3 minus sigma 1 square base, this will also goes to 0. I get sigma 1 square. So because here square is there, the negative sign will cancel out. So I'll get this sigma 1 square. So if I expand this, what I'll get? 1 plus nu by 6E So here you have sigma 1 minus sigma 2 whole square. So then what I'll get here, sigma 1 square plus sigma 2 square minus 2 sigma 1 sigma 2. If I expand this sigma 1 minus sigma 2 whole square, if I expand it, I'll get this. Plus I have one more sigma 1 square plus sigma 2 square. So that means if I simplify this, what I'm going to get? 2 sigma 1 square, 2 sigma 2 square minus 2 sigma 1 sigma 2. So that means I have 2 is there. I can take the 2 is common throughout. So then what it will become is 1 plus nu divided by, so the 2 into this 6 cancel out. Then I'll get 3e into sigma 1 square plus sigma 2 square minus sigma 1 sigma 2. So this is the expression for the distortion strain energy in case of biaxial state of stress. Now if I want to take uniaxial state of stress, in case of uniaxial state of stress, even your sigma 2 is also 0. For biaxial, triaxial, all three will be there. Sigma 1, sigma 2, sigma 3 are there. So in case of biaxial, your sigma 3 is going to be 0. Then in case of uniaxial, even sigma 2 is also 0. This is also 0. This is also 0. So then what I get in this expression, I need to put sigma 2 is 0. So if for that, what I get? 1 plus nu by e, 3e. So this is 0. Even this is also 0. So what I left with is sigma 1 square only. So this is the expression for biaxial state of, uniaxial state of stress. So like this, I can calculate or I can derive the strain energy, distortion strain energy in case of triaxial, biaxial and uniaxial. So now to define our failure theory, so we need to make use of this and we try to derive the failure equation. So therefore, this is our strain energy for unit volume, distortion strain energy for unit volume. So now this we need to equate it to the strain energy in the simple tension test. So in case of simple tension test, you have only sigma 1 is the stress. So the failure criteria is sigma 1 should be equal to S by T. So now if I do that, just now I shown you what we got in case of unidirectional uniaxial loading, 1 plus u by 3 into sigma 1 square. So in that case, or else here also you can see I need to put this one is 0, this one is 0, this one is 0, even this one is 0. All these are 3. What I left with? Sigma 1 square here, sigma 1 square. 2 sigma 1 square means 2 and 6 cancel out. You will get 1 plus nu by 3e sigma 1 square. Sigma 1 is nothing but S by T. So therefore, this is the distortion strain energy in case of your tension test. So then we need to equate these two so that is going to be our failure equation. So that's what the criteria of failure of distortion energy theory is expressed as this strain energy, distortion strain energy should be equal to this distortion strain energy. So now from this I can simplify this equation. Sigma v 1 plus mu 1 plus t will cancel out. So E will cancel out here, and so 3E here. This side 6e, so here I'll get only 2. So from that I can write the failure equation. So this is going to be the failure equation. If I simplify that, so this is going to be the failure equation. So for triaxial state of stress, or if I want, I can further simplify this. So just I'll bring this 2 to this side and I'll write in terms of SYT. So if I write SYT as, so if I simplify this one further, I'll get this is going to be the failure equation or design equation, I can say, for distortion strain energy in case of triaxial loading. Suppose from this, if I want to derive for a biaxial state of stress, simply I need to put sigma 3 is 0. For a uniaxial state of stress also, simply I need to put sigma 2 is also 0. So now if I want to introduce factor of safety also into this, so now this SYT will be replaced by SYT by FS. That is the only difference you need to consider. If you want to introduce factor of safety also into your design, you need to replace SYT by FS. So that's it. So this is the how you can, this is going to be the design equation or failure equation for, or generally we call it as design equation for a distortion energy theory. So in case of biaxial state of stress, like I mentioned here, in this equation, just simply you need to put sigma 3 is 0. So if you do that, you are going to get this one. I already shown to you how you got this expression. So SYD by Fh is equal to sigma 1 square plus sigma 2 square minus sigma 1 sigma 2. So this is going to be the expression for our design equation for a biaxial state of stress. So now once you have this equation, now I want to plot this equation on a sigma 1 sigma 2 graph. So if I plot that, you will get ellipse as your failure region. Okay. Okay. So before going to that, so earlier in case of maximum shear stress theory, we predicted that the shear strength has half of the yield strength. So here in case of this distortion energy theory, what is the shear strength? So why we are concentrating here shear? Because of distortion, what is happening? There is a change in the shape. So this change in the shape is because of this shear stress only. So therefore, if you are able to find out what is the equivalent shear stress of this distortion energy theory, so directly you can use that. If it is subjected to only pure shear stress, so instead of applying all these equations, you can directly use those formula to compute the dimensions of the component. So now, if I say only pure shear means you can see the here state of stress here. You don't have any normal stress here. I have only tau xy. So in case of pure shear stress, what is your sigma 1 and sigma 2? Sigma 1 is equal to minus sigma 2, which is only you'll get tau xy only. So if you recall your formulas for the maximum principal stresses, that is the formula for maximum principal stress is sigma x plus sigma y by 2 plus or minus. Plus sign will be used for the maximum principal stress and minus sign that is for sigma 1, minus sign will be used for sigma 2 value. So plus or minus square root of sigma x minus sigma y by 2 whole square plus tau xy square. This is the formula for computing the principal stresses. So now in this formula, I will apply this formula. So here I will write sigma 1 comma 2 equal to. So to compute sigma 1, I need to use plus. To compute sigma 2, I need to use minus sign here. So now I'll use this is the state of stress. So for this state of stress, what is the value of sigma 1? There is no normal sigma x. There is no normal stress. So sigma x is 0. Even if I don't have any sigma y, normal strain in the y direction, that is also 0. So that means this is 0. This entire term is 0. Only I have this. So that means what I left with, so this entire term goes to 0. Here I'll have plus or minus. Then tau xy square under square root. Square and under square root will cancel out. What I'll get is only tau xy. So plus or minus tau xy. That means your sigma 1 is plus tau xy. Sigma 2 is minus tau xy. So that is what I'll call it as a pure shear stress. So because it is subjected to only shear. So in this case, so I want to find out what is the one measure stress. So we'll call that as one measure stress also. Earlier, whatever expression we derived it, so that we'll call it as a one measure stress also. So in this case, I want to derive what is the one measure stress. So this is what just now we derived. So in case of a pure shear state of stress, your principal stress is sigma 1, sigma 2 is plus or minus tau xy. So then if that is the case, if I take this and if I substitute into this equation, that is the failure equation or design equation for a one measure stress, then what I'll get? So here, if you look at here, sigma 1 is tau xy, sigma 2 is tau xy. So therefore, what will get? Sigma tau xy square plus tau xy square. Sigma 1 is plus tau xy and sigma 2 is minus tau xy. So the minus will become plus. So this is also tau xy square. So what I'll get is 3 tau xy square. So if I substitute for sigma 1, sigma 2 in this expression, what I'll get is this is equal to square root of square root of 3 tau xy. So now if I want to rewrite this, I can write this one as root 3 times tau xy. So square root and square will cancel out. What I'll get is root 3 tau xy. So this tau xy is nothing but your SYS, that is yield strength in shear. So which is equal to your SYD. So that means if I take SYD is equal to 3 times SYS, root 3 times SYS, or else from this I can write SYS is nothing but 1 by root 3 into your SYD. So see, you are getting a different expression for the yield strength in shear and for distortion energy theory. In case of maximum shear stress theory, you got it as SYD by 2, whereas here you got it as 1 by root 3 into SYD. So this 1 by root 3 is nothing but, if you calculate that, you will get it as 0.577. So whereas in case of maximum shear stress, you got it as 0.5. In this case, you are getting 0.577. So that means this distortion energy theory predicts higher value for the shear strength for a component when compared to the maximum shear stress theory. So that's what I've shown here in these slides. So whatever we discussed, so this is sigma 1 is equal to sigma 2 is equal to tau xy. So then, so if you apply, if you substitute this tau xy into your design equation, we get SYD is equal to root 3 tau xy. This tau xy is nothing but the shear strength in yield, so which is 1/3 of SYD, which is nothing but 0.577 SYD. So this is the shear strength in yield or at yield according to this distortion energy theory. So now, therefore, according to the distortion energy theory, the yield strength in shear is 0.577 times the yield strength in tension. So whereas in case of the maximum shear stress theory, here instead of 0.577, you have only 0.5. So that means your maximum shear stress theory is predicting less strength when compared to this distortion energy theory. So then, if I go for the, if I plot that failure region for this, okay, so that is, this equation is going to be the, if you take it, it is a second order equation, and also if you simplify this equation, you can show that this is the equation of the ellipse. So with S, this ellipse will have two, one is major axis, another one is minor axis, and this major axis, minor axis, semi-minor axis, and the major axis dimensions are given by like this. So this is going to be the semi-major axis dimension, and this value is going to be the semi-minor axis. So that means, so here I got the shape of the curve for this distortion energy theory is going to be a elliptical shape here with, so here you can see that here. So this is the expression of what we got it. So if you rearrange this and if you can convert that one into equation of ellipse, so something like x by a whole square plus y by b, y by b square is equal to some a square, something like that. I can modify this so that if I do that, that a and b are nothing but our semi-major axis and semi-minor axis. So those values are going to be something like this. So now I got the failure envelope for this distortion energy theory. So again in this, if your design point, so that means for a given component, if you are finding sigma 1 and sigma 2, if you mark the values of sigma 1 and sigma 2 for a particular point, let us say if it is false like here, the design is safe. Or not only that, anywhere within this envelope, if the point lies, then the design is safe. If the point falls outside this envelope, then the design is, or the component is going to be failed. So this is a failure criteria for the distortion energy theory. So here, this is the final note we have. Experiments have shown that distortion energy theory is in better agreement for predicting failure of ductile materials or ductile components than any other failure theory. So that means the most suitable or most appropriate failure theory for ductile materials is distortion energy theory. Of course, so we'll use maximum shear stress energy is also maximum shear stress energy theory also, but the only thing is, say just now we are saying, so maximum shear stress theory is predicting only shear strength as 0.5 times yield strength, whereas this theory is predicting the shear strength as 0.577 SYD. So that means it is predicting the better value compared to that. But the only thing here is, so simultaneously people are using both the theories, but the drawback with this theory is here the calculations are complex. In case of distortion energy theory, the calculations are complex, whereas in case of that maximum shear stress theory, the calculations are very easy or simple. So that is the one difference. So if you want to use, if you want to have some solution are not that much accurate, But if you want to have a quick solution, we'll go for maximum shear stress theory. Or else, in other side, if I want to have an accurate solution, I don't bother about the complexity of the equations. If I want to have an accurate solution, I will go for this distortion energy theory. So both are applicable for ductile materials or components made of ductile materials. Whereas the first theory what we discussed, that is Rankine theory, that is applicable for brittle materials. So now, once you understand all these principles of these three failure theories, we are not going to discuss the remaining two, that is maximum strain energy, maximum normal strain theory and total strain energy theory. So we are not discussing because they are not practical use, they are not in practical use, or they are not giving or predicting any proper results for any component, whether it is brittle or ductile. So those failure theories are not predicting the proper results. That's why people are not using those things. So those theories are only for academic purpose. That's why we are not discussing those things also. So now we want to compare all these three, whatever failure theories we study, we discussed now, we'll try to compare all those three on a single curve, something like this. So that means if I superimpose all the failure envelopes of those three failure theories, so then I'll get, this is the shape. So now this is the square, which is for Rankine theory, and then you have a hexagon, which is shown as a dotted lines here, that is going to be the maximum shear stress theory. Of course, this is there, whatever ellipse is there, this ellipse is for the distortion energy theory. See, that's what is shown here. This is maximum principal stress theory, and this is the distortion energy theory, and this ellipse and this dotted line is going to be maximum shear stress theory. And also here, if you draw shear line in case of pure shear, so this is our principal planes, sigma 1 and sigma 2 are the principal planes. So if I draw a line at 45 degrees, this is the plane of maximum shear stress. So that's why we'll call it as a shear diagonal also here. So then on this line, so here you can clearly see that, so this value and this value, there is a slight difference here. So that difference is nothing but 0.077 SYT. So here this value is 0.577 SYT, whereas from the maximum shear stress theory you are getting 0.5 SYT. So, and also not only that, so from this we can observe some points here. Suppose if I design a component, if I design a ductile component, so based on the maximum normal stress theory, suppose if I have a design point which is like this. So now if the design point like this means according to your maximum normal stress theory, it is within the failure region only. So this square is the failure region or failure envelope. If I take the point here, so according to this one, it is still your design is safe. But according to these two theories, it is not going to be safe. That means the component is going to fail if the point is less, because the point lies outside the envelope of failure envelope of these two theories. So that means, so this is even, so that's why this is not, this maximum normal stress theory is not used for ductile materials, because it is not predicting the failure for the ductile materials properly. So that's why these two theories are most suitable for the ductile materials. So I'll summarize all those points here now one by one for all the, based on all this, so far whatever we discussed on these failure theories, that is summarized here. So ductile materials typically have same tensile strength and compressive strength. So that's what we already discussed. That is SYD is the same as SYC in case of ductile materials only. In case of brittle material, it is different. So ultimate strength in tension is less than ultimate strength in compression. That also we already discussed. Also, yielding is the criteria of failure for the ductile materials. This is what we already discussed. In maximum shear stress theory, the distortion energy theory, it is assumed that yield strength in tension is equal to the yield strength in compression. Same. So it's because these two theories are used for the ductile materials. So just now we written here for ductile materials, these two are same. So these two theories will also assume the same thing. SYD is same as SYC. Also the failure of criteria is yielding. So that means what you want to say here is these two theories are most suitable for the ductile materials. Therefore, maximum shear stress theory and distortion energy theory are used for ductile materials. Then next point is distortion energy theory predicts yielding with precise accuracy in all four quadrants. See, you can see that in all four. See, only if you take that maximum normal stress, maximum shear stress theory, it is predicting only properly in the first quadrant and third quadrant only. So here the other two, sorry, second and fourth quadrant only. If you take first quadrant and this third quadrant, so your maximum shear stress theory is same as your maximum normal stress theory. Both are same only. So you are only in this quadrant, maximum normal stress theory and maximum shear stress theory, both are same. So therefore, it is not predicting the failure properly in case of this ductile materials. So only in two quadrants it is predicting properly. In other two coordinates it is not predicting properly. So therefore, only the theory which predicts a failure in all four quadrants properly is the distortion energy theory. So the design calculations involved in this theory are slightly complicated as compared to those of maximum shear stress theory. That's what I already told. Here the equations are somewhat complex or complicated when compared to the maximum normal stress theory. That's our maximum shear stress theory. So the hexagonal diagram of maximum shear stress theory is inside the ellipse of the distortion energy theory. Clearly you can see that. So the maximum shear stress theory, the bounds of the maximum shear stress theory is within the ellipse only. So that means here you can see that suppose if I have a design point here, so for this design point, this theory, that is distortion energy theory, will say that your design is safe, whereas your maximum normal stress theory and the maximum shear stress theory will say that the design is going to fail. So that means here these two theories are not predicting, or else your distortion energy theory is predicting it properly. So therefore, maximum shear stress theory gives results on conservative side. So that's why it is assuming maximum normal stress theory, your area here, the maximum allowable area is less when compared to the ellipse. So that means here it is assuming more factor of safety when compared to the distortion energy theory. So that's why we'll say it is a on conservative side. The maximum, when you compare maximum shear stress theory with distortion energy theory, maximum shear stress theory is a conservative one. So on the other hand, distortion energy theory is slightly liberal. So similarly, one more point, the graph of maximum principal stress theory is the same as that of the maximum shear stress theory in the first and third quadrant. We already discussed in first quadrant and third quadrant. Those two theories are same. However, maximum, the graph of maximum, okay, so maximum principal stress theory outside in the third and in other two quadrants. If we say second and fourth quadrant, the maximum principal stress theory is outside the ellipse of the distortion energy theory in the second and fourth quadrant. So they are outside of your ellipse. So thus it would be dangerous to apply maximum principal stress theory in this region, since it may predict the safety when in fact no safety exists. So that means here you can see that here this is the second quadrant and this is the fourth quadrant. So in this, your maximum normal stress theory region is up to this point, like I already explained. So it falls outside this failure envelope here, in both these quadrants. So this envelope is beyond this failure envelope. So therefore, if the point is here, this theory, maximum normal stress theory, are here, the maximum normal stress theory is saying that the design point is safe according to this theory, but according to this theory it is not safe. So actually this is not safe. So therefore it is very dangerous to use this maximum normal stress theory when the design point lies in second and fourth quadrant. So then next point comes, the maximum shear stress theory is used for the ductile materials if the dimensions need not be held too close and generous factor of safety is used. Like that, already told. So maximum shear stress theory is assuming a generous factor of safety when compared to the distortion energy theory. So the calculations involved in this theory are easy than those of distortion energy theory. So only thing is, the advantage of this maximum shear stress theory is the calculations are little bit easy in case of maximum shear stress theory when compared to the distortion energy theory. So similarly, the compressive strength of a brittle material is much higher than the tensile strength. This also we already discussed. Therefore, the failure criteria should show a difference in the tensile and compressive stress. On this account, maximum principal stress theory is used for the brittle materials. Also, brittle materials do not yield and they fail by fracture. So we already know this one also. So like this, so we can compare all the failure theories, and also we can summarize all these failure theories and in what situation, what type of failure theory we need to use. So that is purely based on the type of material, and also first thing is, if it is a material is brittle material, you have to go for maximum normal stress theory. If the brittle is material is ductile, either you can use maximum normal stress, maximum shear stress theory or distortion energy theory. Again, in those two, if you want to make a choice, if you want to calculate the accurate dimensions, you have to go for distortion energy theory. So if you want to compromise on the accuracy, but still, if you want to design for the ductile materials, so with less number of calculations, you go for this maximum shear stress theory. So this is about this failure theories. So I'll stop at this point today. So in next class, using this failure theories, how we can design the component, that we'll see in the through some solved problems in the coming classes. So before going to close this class, so if you have any doubt, then we can discuss our doubts so that I can clarify our doubt. So we'll close the class also. So if you have any doubt, you can ask now. If everything is clear, then it's okay, no issue.